So in 1979, Vorst conjectured the following thing, that if R is a commutative algebra, say finite over a field, dimension D, then if Kn of R is the same thing as Kn of R T1 through Tm for all m. So this is the condition that he called K-regular. Kn regular. And n is bigger than the dimension of D, then R is regular. So his evidence of this was that he could understand curves. And as usual, once you understand what's going on with curves, you think you understand everything about algebraic geometry. So in 2008, Bridget, you set a terrible precedent for me. Now I have to do this. Cortinius, Hazelmeyer, and myself, based on work with C.H., W, and Schlichting, and later Walker. So you see, it's comparable. Okay, so based on all of this, we did the case where the characteristic of K is equal to 0, and it's true. And moreover, we showed that this thing was equivalent to saying that the K-theory of n of R is isomorphic to the K-theory of n of R when join one variable for all n less than or equal to D plus 1. And then later, so 2013, Geisser so we proved the conjecture and characteristic 0, and they proved the this is any characteristic. Did I finish spelling Hessel? Yes. Prove the characteristic K equals to P, strictly positive case. And in both cases, the key trick is the following one. So if R is a regular local ring, is local of dimension D and not regular, so there's a sequence of elements A sub, let's do 0 to AD, which are linearly independent over when you pass to our modulo the maximal ideal. So this is just if they're not regular, then there exists a bunch of things, because not being regular means that when you go modulo them, take the maximum in m mod m squared. Yes? Yes, that's true. So just to make a small joke, if you restrict yourself to curves, you have resolution of singularities. Therefore, one should not worry. Yeah, so the point is that if your ring is regular, then the m mod m squared is a vector space of dimension d. And if it's not regular, then the dimension of this is bigger than d, so you can find d plus 1 linearly independent variables. And then the point is that omega to the d plus 1 of r over k is, well, here you have d of a0 wedge, d of a d, and here is non-zero. And so that's the trick, along with the fact that the Kähler differentials are sitting in the Hochschild homology. So this is the key trick, and it's going to be buried in my lecture, so you're probably not going to see it where it actually shows up, unless I remember. But anyway, I want to give you a counterexample. For non-affine varieties. So this is a really terrible idea of mine, and that's I'm going to try to draw a picture. So this is supposed to be the Möbius band over the circle. And somewhere in the middle of this Möbius band we have the middle stripe. So, so yeah. So in here we form the cut. So let's call this thing x tilde, and then we pass this to a parametrized cusp. We'll call this x. And so what you basically do is you take a line and then you just pinch the center and make a cusp. But you see what's happening is because of this twist, that it's not going to be a product of things. So if I'm going to do this, I have to tell you what line bundle I'm going to be working with. And so this is an elliptic curve. And so you take O of P minus Q. And then what you do is you take the line bundle associated to this, or the P1 bundle. It doesn't really matter. So you take 2 points on the elliptic curve. The difference between them is the divisor of degree 0, and if P minus Q has infinite order in the Picard group of the elliptic curve. So this is the technical condition that gives this. And now one of the ways that you can think about this is that if you think locally on the base, this line bundle is trivial. And when the line bundle is trivial, this is what you have. So E is spec of R. And A is spec of R T squared T cubed. Okay, so that's the way that you form this cusp. And what I want to claim is that you can actually do this computation. So now I'm going to write down something horrible. So the K-theory of this cusp ring was calculated a long time ago, It was based on a conjecture, which was later proven by Cortinius in, I think, 1998. Mathematische Nauen Zeitschrift, Krella. And in order to formulate this, what I should do is tell you the local version. Google him. Okay, so the local version of this, the way that one thinks about this is that you have a line bundle, and locally you replace the polynomial ring by the symmetric algebra over R in L. So this is R plus L tensor 2 plus L tensor 3 plus blah, blah, blah. So it's very much in the spirit of what Richter was doing in the last talk. And then A is R L squared and L cubed. So if you want to keep track of the way that this is moving around, you do it in terms of the line bundle. Okay, so the calculation so let me write it this way so we don't have any confusion. And I'm just going to do some of this. So there's one factor, and then there is, let's see, L to the 5 plus L to the 6, tensored with a huge sum, and I guess that I'm going to copy it because I'm never going to get it right if I don't. Plus L to the 6 times I minus 2, tensored with omega squared of R, plus R, tensored with omega n minus, well, yeah, n minus 2 of R. And there's a similar formula, well, for n odd, but I'm not going to worry about it because I just wanted to give you the idea that this is a fairly nasty computation, which was done by using the idea of Hochschild homology over a simplicial ring and then looking at the spectral sequence for the simplicial ring. And so we get explicit generators back in 1989. And if you take the explicit generators and you read through the calculation again, you get this. Oh, L is the line bundle O of P minus Q restricted to spec of R in my application. But this is a formula which is true for any line bundle. Now I have to be careful. Algebraic geometers refer to a line bundle as a physical object, and this should be a sheaf. But since I'm talking about this is any rank 1 projective module. So this is the formula that we got back in 1989, jazzed up to be modern. Two I minus 2. N is the subscript on the K-theory. Now the point of this is that in this particular case, all of the cohomology on E with coefficients in L tensor anything is 0. And Kähler differentials of R is isomorphic to R. So this is the Kähler differentials of R over the field K. So if you read this, what this says is that the K-theory sheaf of OE, now I have a line bundle, so let's say L is equal to the line bundle O of P minus Q on E. So then here we have L squared and L cubed. And just because it's annoying, I'm going to mod out by the K-theory of OE. And so then these are all sums of powers of this line bundle, which has no cohomology. Now, sorry? Yes. And the point of writing down the explicit formulas, you can see that there's no occurrence of j equals 0. There's only occurrences of j equals 1 and possibly 5 and 6, and then lots of higher powers of L. Okay, so the point of this is that there's a Zariski descent spectral sequence. So the Zariski descent spectral sequence basically tells you that the HP on E with coefficients in these things is going to converge to the K minus P minus Q of, X relative to the P minus Q of E. So this is K minus Q. And the point of this is that I just wrote down what all of these things are, and then I didn't write down what there is, but there's a subscript here which is supposed to be 2i or 2i minus 1. When you take the cohomology, everything dies. So the point is that the K-theory of X is the K-theory of E. And if you replace E by E cross an affine space, well, E is a regular smooth variety, so when you cross it with an affine space, it doesn't really change anything. If you actually take this and you replace R by a polynomial ring in R, the basic calculation doesn't change. And this is the same thing as K-theory of X cross affine space M for all M greater than 0. So this is a counterexample to the conjecture for non-affine varieties. The point is that these conditions of K-regularity are satisfied, but the ring is not smooth because its singular locus is that little dotted pinched line in the middle, the cusp line. So it has a singularity of codimension 1. And so the point is, how do you deal with an example like this? So now I can tell you what our theorem is. Aha. Just in case. Willie has actually seen me perform acrobatics to reach boards. Maybe before I tell you the theorem, maybe I should make an observation. One of the things that you can do is you can look at other line bundles. And one of the line bundles on E is just the line bundle that you get corresponding to, let's say, the base point of the elliptic curve. And this is ample. And so if I take the line bundle here, that means that L is symmetric algebra over OE of OE O of Q. So the notation looks horrible, doesn't it? But that's the formal way that, for example, if you picked up Hartshorne's book, that you would write down that line bundle. So passing to this line bundle, locally it's the same thing as what we've just done here. The difference is, when we do that, erased all of those marvelous little copies of L tensor blah blah blah. But you remember that there were lots of copies of L tensor blah blah blah, and one of them was just 1L. And when you tensored that 1L, P minus Q, tensor with O of Q, you get O of P, and this has non-zero cohomology. So then what you get is that the K-theory of X, K-theory of X is not the same thing as the K-theory of L. For example, for star equals to 0. So this is an example where the condition that we had failed. Okay, so now I can now that you sort of understand what might happen, there's a colored chalk somewhere? It's the redshift. Okay? Okay, so the point is, this is a joint with Hasemeyer. So let X be quasi-projective. Over a field of characteristic 0. And before I go any further, I'm going to say the following thing. Probably this theorem extends the characteristic P, but the techniques that you would need to generalize at the characteristic P are the sort of techniques that Birger was talking about, and they're much different than the kind of techniques that I'm going to show you. So probably it would extend, but you'd need a different technique. Probably one along the lines of Geisser and Hesselholt. Okay, so if Kn, well, Ki of X is, let's see. So I didn't tell you what L is here. L is going to be line bundle And now I want to make one short point, and that is that if you have a quasi-projective variety, by definition it's endowed with an ample line bundle. So that hypothesis is just used to get that. So just as an example, in particular, what happens if ki of x is isomorphic to ki of L for all I less than or equal to d plus 1, then it's regular in codimension d, and it's a d-dimensional variety. So x is regular. Any one. Fix one line bundle. All you need is one line bundle. Now in the affine case, this theorem is also true, but in the affine case, where x is spec of a ring, the free module of rank 1 is also an ample line bundle, and then you recover exactly this result that we had before with the polynomial rings. So what this suggests is that somehow or other, this notion of K-regularity, which just depended on extensions by polynomial rings, is something which works for affine varieties, but if you go to projective varieties, you have to be, we need a new notation. Okay, so here's an example. If x is a surface, and ki of x, ki of x is equal to ki of L for all I less than or equal to 2, then x has, at most, isolated singularities. So the point of this is that here is an example of an application of K-theory to something which has nothing to do with K-theory. You start off with something in algebraic land. Here you have an ample line bundle that's completely in algebraic land. Here you have a K-theory criterion to tell you something about something in algebraic geometry land. So that's why I like these kind of theorems. They're useful when you're talking to funding agencies, because you can say that what you're doing is worth something. Okay, so so the technique is to use CDH descent, which is essentially model theory. Cohomology, Serre's theorem B. And the definition of ample. And then Hochschild homology. So there's a diagram, but without thinking about the diagram, there's Hochschild homology of n minus 1 of a ring, mapping to the cyclic homology n minus 1 of a ring, which maps to the negative cyclic homology in n minus 1, which maps to the K-theory in dimension n. So this is essentially the trace map that Birger was talking about, jazzed up to take account of the circle action. And these are canonical things in cyclic homology. This is, for example, this is the I map in the Kunz along exact sequence. Okay. So I need to spend about 10 minutes telling you about what these words mean. Serre's theorem B is something I was going to do in 15 minutes. But Serre's theorem B basically says that if you have a coherent sheaf over a, well, let's say quasi-projective variety, and an ample line bundle, and you tensor with the ample line bundle enough times, then, well, I'm going to get this wrong, but two things are true. It's generated by its global sections, and the higher cohomology vanishes. And so both of those facts are going to get used. Yes. This is an N. And as the map goes this way, doesn't it? Okay, so the basic picture is that you have HCN minus 1 goes to HN, N goes to HPN, goes to an S map, HCN minus 2, and so on. This goes down to an HH. This is essentially what Bridget was talking about. What? You're right, it was not red, but it was a shift. I'm not telling you what these things are. So this KH is not the Hermitian K-theory of yesterday's lecture. And then this is something which I'm going to write FK just because I don't want to have a name for it until I've actually produced it. So back in the 1980s, I used the unfortunate notation of K-nil, or nil. And then I got confused with lots of other things, and then I tried calling it K-rel. But then Karoubi and Cones used K-rel for something in a completely different context, and so that was a bad notation. So F sub K is something that you'll see in a little bit more broader situation, but it's just a sort of an ad hoc notation. So, so the point is, this row is all topology. And so example is that Kn is pi n of some spectrum K. But down here, this is all homological algebra. And the idea is that pi n of an H, well, let's not use H, pi n of a chain complex C is the same thing as H minus n of that same, of X on that chain complex. So when you convert from topology to cohomology, the subscripts of an n turn into superscripts of minus n's, and the minus signs give you a little problem. If you keep track of them, you're fine, but if you are not keeping track of them very carefully, then you sort of end up with this plus or minus issue. But that's the basic topology. And here is a big theorem. This is Cartesian, Homotopy Cartesian. So, well, just a second. And now the thing that goes here, I have to explain. So here's an X that I forgot. And this square is Homotopy Cartesian. So what do I have to explain? I have to explain homotopy K-theory, and I have to explain this weird thing. So the first one is easy to explain. This is essentially so if you I don't need the boundary. So there's a simplicial ring, which is a co-simplicial ring, which is x cross A1, x cross A2. And so what you should think of, this is an algebraic variety for the one simplex, and this is an algebraic variety version of the two simplex, and so on. So this is a co-simplicial ring. When you apply K-theory to it, you get a simplicial object, and now you take the realization of that. So that's a definition. It doesn't tell you much. But here's a fact, and this is due to Hasemeyer. But there's a fancier version, which has recently come available, which is due to Denis Charles Szynski, which uses the adjective infinity dash in front of lots of words. This is pure algebraic geometry. This is using stable infinity categories. So what is the fact? The fact is that kh of x is the same thing as this weird CDH of x with coefficients in k. So if you make that substitution over here, then what you see is the Cartesian square is some functor, the CDH version of that functor, some functor, the CDH version of that functor. And then the point is that if I do HCN minus 1, okay, so here is a shifting convention. So this is basically suspension so that I get the indices working out right. Here's the CDH version of x with coefficients in HC with a shift, and the shift comes in and out of this operation, and that is Homotopy Cartesian. And then here is the one with, yeah, let me just stop there. So the point that I'm trying to make is that if you're trying to understand this, you want to take the fiber here and compare it to the fiber here. And so if I make a definition, if I have f sub a is the homotopy fiber of the functor which goes from f to the CDH, whatever this is, then here I would have f sub k, and this is my fibration square that I was writing there. Here I have f sub hn, and here I have f sub hc with a shift. So now I've constructed a diagram where the rows are fibrations, sequences, and because this is a homotopy Cartesian square, these are the same, and because this is a homotopy Cartesian square, these are the same. Sorry, what? Yes, this is in that paper. Okay. Yes? Let me define it now. So, so first of all, I want you to believe me that there's a topology called the CDH topology, and it's related to the Zariski topology, and there it is. Because otherwise I'd run out of time and not get to anything interesting. So, okay, so there's a model structure on pre-sheaves of spectra on the category of schemes essentially a finite type over a field K. And so So there's a local model structure. Let me just cut to the chase. The weak equivalences, so you have an E and you have an F. And that means that if you take the sheaves, so if I take a pre-sheaf with spectra, that's a contravariant functor from varieties, schemes, contravariant functor from schemes to spectra. I take homotopy groups, I get a contravariant functor from schemes to abelian groups or maybe graded abelian groups. I can sheafify this, and then I want to say that this is are isomorphic. So that's the definition of weak equivalence. And now you can, once you have that, in order to form the homotopy category, you don't really need anything more, but I will give you some more. The cofibrations are for every x, e of x to f of x. So now this is a contravariant functor to spectra. That means this is a spectrum, that's a spectrum, this is a map of spectra, and this is a cofibration of spectra. So Shane would say this is the CDH local injective model structure, right? Words like that, okay. So definition, the fibrant replacement of E is H CDH blank E. So fibrant replacement means the following thing, that you factor, and I'm writing star, but if you were doing based guys, you might want to write something else. Anyway, you factor this as E into an H, and then fibrant like that. So the point is that this is fibrant, and it's equivalent in this, it's weak equivalent in this sense. So that's what H is. And so that explains this theorem right here, because this is a spectrum. K-theory is a spectrum. This is a fibrant replacement of K-theory. And so that's all making sense. But now I want to just point out that in homology, if E is coming from a chain complex, so if you have a chain complex, there's a construction which Bridget referred to, and that is essentially that you do a series of truncations, and then to connect simplicial objects, then you take the realization of these simplicial objects, and that gives you a topological space, and the series of truncations gives you a Whitehead spectrum. So if E is a topological space coming from one of those things, so let me call it a chain complex E. Now I am in cohomology land, so I'm going to index the chain complexes as cochain complexes. Then H of E, well, let's put an X here. Well, no, yeah, let's put an X here, is I dot of X, where E to I dot is an injective resolution. So technically, if E is a sheaf concentrated in 1 degree, this is an injective resolution, but if it's a chain complex, then what you need to do is to take a Cartan-Eilenberg resolution and take the total space to get something that you can call it an injective resolution. So this is what's going on, and the point is that the homotopy groups of this topological space turn out to be the hypercohomology groups of this guy. So what I've done is neatly translated everything from the language of topological spaces to the language of chain complexes and cohomology of varieties. Okay, so here is a new piece of chalk, and there is no place to write. Okay, so here's a marvelous thing about line bundles. You've taken injective resolution and you tensor it termwise. With a line bundle, you get an injective resolution. And that's not something that they teach you normally, but if you think about it, it's actually fairly trivial. The point is that a line bundle, invertible sheaf of rank 1, is locally free. So if you tensor some sequence, it becomes exact. But because it's a rank 1 projective, it's invertible, there's an inverse. And so if you then tensor with the inverse, you get back to where you started. So if you take the lifting property that defines injective resolutions with an I tensor, and then you just tensor with the inverse of the line bundle, you get an injective property. So you get a map that exists, and then you tensor back, and you get this. So the point is that I can sort of tensor with the line bundle in and out with relative freedom. And there's another thing that is technical, but also at a fairly elementary level. And that is that if you take a CDH sheaf, you think about it as a Zariski sheaf, you tensor it with a line bundle in the Zariski sense, then it's actually still a CDH sheaf. So there are little tricks like this that I'm sort of like sweeping under the rug. Okay, so I'm going to write down some spectral sequences, and what I want is the spectral sequences of coherent sheaves. And the problem is that if I don't have finite transcendence degree, then they aren't spectral sequences of coherent sheaves, so you have to reduce to something of finite transcendence degree in order to make that problem go bye-bye. Then the second thing is that because of all of these diagrams, what you want to do is sort of like not think about the right side of the diagram, but think about the left side of the diagram, and that reduces you down to the fiber for cyclic homology. And if you sort of play with the SBI sequences, you can sort of get everything down to the fiber for Hochschild homology. And so then you get things like this. So I'm going to write Zariski because I've been confusing you with what topology I might be in. Now, because this is going to come up a lot, I'm just going to write this kind of notation. So this is what needs to be studied. Okay, so then the Knuth formula for Hochschild homology which basically says that the Hochschild homology of a ring tensor with a Hochschild homology of, let's say, a polynomial ring is the same thing as the Hochschild homology of R adjoining the polynomial ring, the tensor product of the two rings. And I'm using the fact that I have a field so that everything is flat, so that I don't have to worry about these I don't have to mutter cofibrant in the same way that that you had in the last talk. So using this what you see is that is you see that there's a formula that looks like that. So the point is that if you want to look at the Hochschild homology of R with coefficients in a line bundle, it doesn't fall into the Knuth formula because L is not defined over a smaller field. But you can pull a trick, and that is that so you have the Hochschild homology. Well, so there's an L, an R tensor L in degree 1, and there's an L in degree 0. In the Hochschild complex for RL, and then you can just write down maps. So the Hochschild homology of a polynomial ring in one variable is given by Qt in degree 0 and the Kähler differentials of Qt in degree 1, which is isomorphic also to Qt. And I have maps of those two factors in coming from exactly this. And so therefore, you get the same formula for this. And R is going to be the coordinate ring of the elliptic curve. L is a line bundle defined over R. And so RL means R plus L plus S2L plus, right? So it's the thing that's locally a polynomial ring. And the point is that if you take these two factors and you map them in, then you get the same factor. So what you end up with is Hochschild homology of RL is isomorphic to the Hochschild homology of R tensored with RL plus the Hochschild homology of R minus 1 tensored with the Kähler differentials of RL over R. And so that's the same formula as the one that you'd get from here. So there's a little bit of a technical dodge that one has to worry about. So now what we want to do is we want to look at the hypercohomology on X with coefficients in the sheaves that we're doing Hochschild homology, right? But I'm actually doing the fiber, so these are the kind of things that we worry about when we're trying to reconstruct things using the hypercohomology spectral sequence. Now the point is partially that HQ of FHH commutes with tensoring with a line bundle, so you can pull the line bundle out. And now the point is that here we have the cohomology on X with coefficients in L to the J, and if you remember what I told Shane, that means that if J is really large, that HP of all of this stuff is equal to 0, for p not equal to 0. And that says that the and h0 of x, coefficients in all of this stuff, is the global sections. And they generate the cohomology on X with coefficients of these H. Okay, so lots of homological algebras going on here. And what we've done is we've basically set ourselves up for the punchline. And the punchline, unfortunately, needs a little bit more space. And more space happens this way. So we didn't use the hypothesis that the K-theory was equal to the K-theory of the line bundle. Kn of x being the same thing as Kn of the line bundle. I guess I had n less than or equal to some number, and the number was n. So I'll change this to an I, just so that I have the same notation I had before. Okay, so that's the hypothesis that I get to use. And if I'm thinking as a topologist, that means the hypothesis that I had basically says that the fiber is n-connected. And what that means is that the fiber with cyclic homology of x, and by the SBI sequence, the fiber for this, whoops, there's an x there, are n minus 1 connected. And Hn, but Hn would be n connected. F. I got FHH on the brain. FK. Thank you. So if this is the same as this, for I less than or equal to n, there's a spectral sequence which converges from the K-theory of polynomial extensions to the homotopy K-theory. And this hypothesis is that the K-theory is equal to the homotopy K-theory in certain degrees. And the fiber has to be then 0 in certain degrees, and that's just the same saying as n-connected. So I'm not writing all of that down on the board because I'm over time. So this says that these things are n minus 1 connected. And that means that the cohomology on x with coefficients in the FHH is equal to 0 for p greater than or equal to minus n plus 1. And now use the homological algebra. That I've done up there, and you plug it all together and you get the proof of the theorem. So I'm sorry that I'm just being very, very sketchy, but I'm also being very, very over time, so I apologize. Yeah.
So, okay.
So the point is that if you're in characteristic 0, there's no difference between the topological versions and the non-topological versions. The THH and Hochschild homology are the same. Okay? So the question that you're asking really would only make sense if you were in characteristic P. And if you're in characteristic P, the whole Homotopy Cartesian square that I wrote down at the beginning doesn't make sense. And you have to replace the Hochschild homology by the TH. Well, you have to replace the cyclic homology by the TC, and the Hochschild homology is, I'm not entirely sure what the corresponding thing is there because you have to do homotopy invariance for the circle action. So I'm not, but there would be definitely something that you could do there. And the comments that I made at the beginning of the lecture that it probably goes through in characteristic P using different techniques is sort of like leading right into this as a homework assignment for you. Good luck. Sorry? Yes, I think you'd have to assume resolution of singularities. Or you could just wait for Hironaka's draft to... Yeah, we really don't know about the resolution of singularities in characteristic P right now. So that's very much in the wind. Yeah.
So does it make sense to ask sort of a complex question? So suppose you have a surface with only isolated singularities.
Mm-hmm.
Can you say something about the K-theory being like not seeing the difference between X and the variable line like L?
Yeah, so what it means is that if it has isolated singularities, then it cannot be... So if X is a surface with isolated singularities, so in particular it's not regular, then K2 of X is not equal to K2 of the line bundle on X. And maybe K1 of X is not equal to K1 of L, and K0 of X is not equal to K0 of L as well.
So like it's widely wrong.
As far as I can tell, yeah. So there's a problem, and that is that Y line bundles you could cross with any locally free sheaf, right? And you can ask the same thing, and I don't know what the analog of ampleness is for locally free sheaves. So that's a technical problem. So, but in fact, here's a warning, and that is that K2 of R equal to K2 of RT does not imply K1 of R is equal to K1 of RT. And so that's a paper with Willie and Christian and Mark Walker that we published maybe 6 years ago. So you have to be careful, and I don't really know a lot of basic analogs, so that's a... But again, if you can do that, that's great. Thank you.